Welcome back. Have you ever wondered how it all began? What existed before the universe? In today's book, A Brief History of Time, Stephen Hawking, the brilliant physicist trapped in a wheelchair, will take us on a mind-blowing journey to the very beginning of everything, the Big Bang, to black holes. So let's start this thrilling journey. We will divide this in different chapters for better understanding. Chapter 1. Our picture of the universe. Our journey begins with a look at how humanity's understanding of the universe has evolved over centuries. Hawking starts with ancient civilizations, where the Earth was believed to be the center of the universe. The geocentric model, with the planets and stars revolving around Earth, was widely accepted until the Renaissance. Enter Nicholas Copernicus, who proposed the revolutionary heliocentric model, placing the Sun at the center of the solar system. Galileo Galilei's use of the telescope provided observational evidence supporting Copernicus, while Johannes Kepler's laws of planetary motion further refined the heliocentric theory. Isaac Newton's law of universal gravitation then unified celestial and terrestrial mechanics, painting a coherent picture of a clockwork universe governed by laws of motion and gravity. Chapter 2. Space and Time. In this chapter, Hawking introduces the groundbreaking ideas of Albert Einstein. Space and time, previously thought of as separate and absolute entities, are now understood to be intertwined in a four-dimensional continuum known as space-time. Einstein's theory of special relativity showed that time is relative and can vary depending on the observer's velocity. This leads to mind-bending concepts like time dilation, where time slows down for objects moving at high speeds. Einstein's general theory of relativity further revolutionized our understanding by describing gravity not as a force, but as a curvature of space-time caused by mass. Massive objects like stars and planets warp the space-time around them, and this curvature dictates the motion of other objects, including light. Chapter 3. The Expanding Universe. One of the most profound discoveries of the 20th century was that the universe is expanding. This chapter discusses Edwin Hubble's observations that galaxies are moving away from us with their speed proportional to their distance, a relationship known as Hubble's law. This finding implies that the universe was once much denser and hotter, leading to the Big Bang theory. Hawking explains the concept of the Big Bang, a singularity where the laws of physics break down, marking the origin of the universe about 13.8 billion years ago. The discovery of cosmic microwave background radiation, the afterglow of the Big Bang, provided strong evidence for this theory, painting a picture of a dynamic, evolving cosmos. Chapter 4. The Uncertainty Principle. We then dive into the quantum realm, where classical physics gives way to the strange and probabilistic world of quantum mechanics. Werner Heisenberg's uncertainty principle is a cornerstone of this theory, stating that it is impossible to simultaneously know both the exact position and momentum of a particle. This inherent uncertainty challenges our classical intuitions and introduces a fundamental limit to our knowledge. Hawking explores the implications of quantum mechanics, where particles exist in a state of probability until measured. This leads to phenomena like wave-particle duality, where particles such as electrons exhibit both wave-like and particle-like properties. Chapter 5. Elementary Particles and the Forces of Nature. This chapter delves into the building blocks of matter and the fundamental forces governing their interactions. Hawking explains the Standard Model of particle physics, a theory that classifies all known elementary particles and describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Particles like quarks and leptons form the matter we see, while force-carrying particles or bosons mediate interactions between them. For example, photons are the carriers of electromagnetic force, while gluons mediate the strong nuclear force holding atomic nuclei together. Despite its success, the Standard Model doesn't include gravity, leaving room for further discoveries. Chapter 6. Black Holes. Hawking's fascination with black holes shines in this chapter. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. They form from the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. Hawking describes the anatomy of a black hole, including the event horizon, the boundary beyond which escape is impossible, and the singularity at its core, where density becomes infinite. He also discusses the different types of black holes: stellar mass black holes, formed from collapsing stars, and supermassive black holes, found at the centers of galaxies. Chapter 7. Black holes ain't so black. In a groundbreaking development, Hawking discovered that black holes can emit radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs are created. One particle falls into the black hole, while the other escapes, making it seem as though the black hole is radiating particles. This revelation has profound implications. It suggests that black holes can lose mass and eventually evaporate, contradicting the notion that they are eternal. This discovery bridges quantum mechanics and general relativity, hinting at a deeper, unified theory of physics. Chapter 8. The Origin and Fate of the Universe. Hawking turns to the grand questions of cosmology. How did the universe begin, and what is its ultimate fate? He examines various models, from the Big Bang to the steady-state theory, which posited a constant creation of matter. The discovery of cosmic microwave background radiation provided strong evidence for the Big Bang, suggesting a hot, dense origin. Hawking explores different scenarios for the universe's future. If the density of the universe is above a critical value, it could eventually stop expanding and collapse in a big crunch. Alternatively, if the density is below this value, the universe could expand forever, cooling and spreading out into a big freeze. He also entertains the idea of a no-boundary universe, where time is finite but unbounded, much like the surface of the Earth. Chapter 9. The Arrow of Time. Time's unidirectional flow, or the arrow of time, is a profound mystery. Hawking identifies three arrows: the thermodynamic arrow, related to entropy, and the second law of thermodynamics; the psychological arrow, our subjective perception of time; and the cosmological arrow, linked to the universe's expansion. Entropy, a measure of disorder, tends to increase over time, providing a direction to the thermodynamic arrow. This increase in disorder is aligned with our psychological experience of time moving forward. The cosmological arrow also aligns with this, as the universe expands, reinforcing the flow of time. Hawking ponders whether these arrows will always point in the same direction, and what might happen if they reversed. Chapter 10. Wormholes and Time Travel. Venturing into the realm of speculative science, Hawking explores the possibility of wormholes, hypothetical tunnels through space-time that could connect distant parts of the universe or even different times. While intriguing, the practical creation and stabilization of wormholes pose enormous challenges, including the need for exotic matter with negative energy density. Time travel introduces paradoxes, like the famous grandfather paradox, where altering the past could prevent one's own existence. Hawking proposes the chronology protection conjecture, suggesting that the laws of physics might prevent such paradoxes by forbidding time travel to the past. Chapter 11. The Unification of Physics. The quest for a unified theory, one that reconciles quantum mechanics and general relativity, is a recurring theme. Hawking discusses various approaches, including string theory, which posits that fundamental particles are not point-like, but rather one-dimensional strings vibrating at different frequencies. String theory offers a potential framework for unifying the forces of nature, though it remains a work in progress. He also touches on other candidates, like loop quantum gravity, and emphasizes the need for a theory that can seamlessly describe all physical phenomena, from the subatomic realm to the vast cosmos. As for the future, Hawking explores different possibilities. Will the universe keep expanding forever, eventually becoming cold and dark? Or will it eventually collapse back in on itself in a big crunch? He also discusses the idea of multiple universes, a mind-blowing concept that suggests ours might not be the only one. A Brief History of Time isn't just about complex physics concepts. Hawking, despite his physical limitations, embodies the human spirit of exploration. He demonstrates the power of the human mind to grapple with the biggest questions about our existence. He encourages us to look up at the night sky with wonder and curiosity, to ask questions and seek answers. That was all for today. Hope you find it informative and interesting, and thanks for watching.